Uh, Hello, my name is Garrett Wibbels, and as part of my work with Dr. Way's condensed matter group, I did a project on influencing crystal growth with external magnetic fields. So crystals seem relatively simple from a certain point of view. They're characterizable essentially entirely by repeating long-range geometric order. Similarly to an ocean, from the surface view, they can be simple, but that conceals a lot of details underneath. So we see this illustrated with a binary solid phase diagram, such as a terbium zinc, in which two metals can give rise to the complexity of a huge, rich number of different phases. And this is also illustrated in figure 3, where with a greater number of constituents, but still the same number, we get different competing phases that can result from a liquid growth. What determines what phase is favored over another is a quantity called the Gibbs free energy, shown here, where a lower Gibbs free energy will be more thermodynamically favored. And this is actually important. This is just generally important and can be seen beyond the solid phase and gas phase. For example, such as the production of ammonia from hydrogen and nitrogen, where state variables can be manipulated to favor ammonia over the other two. And similarly, in a solid phase where we can't really manipulate pressure, we can, however, manipulate something like external magnetic field to favor phases. And this is important because some phases may have more desirable magnetic or electric properties than other ones. And this leads us to what we attempt to do, which is to use this magnet system and integrate it with the furnace system in order to influence growth one way. Now, to do this, we start with a magnet system. We have this long rod system that we put through our bore, and it has a magnetometer that was pre-made. And also on the end, as I zoomed in, we made a Hall sensor that can go beyond the magnetometer's 3 Tesla limit to map out the field inside the bore. After mapping the magnet field, we had to test the furnace and determine that its set point temperature was actually corresponding to a thermocouple temperature inside. So here in figure 2, you see Benny Schundelmeyer, who I worked with, and we moved thermocouple through the furnace as its set point temperature was changing to ensure that the temperatures weren't too divergent from one another. After moving through the furnace, we then actually did a flux growth. Here in the upper left, we see the flux growth crucible apparatus in which metallic components are placed in the bottom, and then we do 2 steps here called necking of an original tube, and then we seal the quartz ampule that was made to be put in a furnace. And after the furnace heats and then recools down, hopefully we're left with an interesting crystal substance such as this iron aluminum crystal. And after a crystal is grown, we do different characterization techniques such as energy dispersive spectroscopy and X-ray diffractometry to determine the composition and structure as well as different properties that may be of interest. We had a lot of different interesting results. So using our Hall sensor, we were able to correlate a voltage to every B field we generated with a simple polynomial fit that was really accurate, meaning that we can go beyond our original 3 Tesla and map for any arbitrary field, accurate field, even without being able to directly see on a screen what the field is. Additionally, I was able to generate this using Python of the homogeneity of the field and the region. We have a really homogeneous region right here, which is more than large enough for a crystal growth. This is a single huge crystal of zinc that we grew from our ytterbium zinc growth, and the individual crystals of the ytterbium zinc were smaller, but not so small that we couldn't do characterization on them. So here are, I did sample 1 and 2. We have EDS data on them, showing that it looks like we have 2 different phases. And then from sample 1, we did additional characterization showing we have magnetization and magnetic susceptibility data of the sample, as well as our X-ray diffractometry correctly showing that we have 2 phases that are in Pearson's crystal database. So the magnet works with a large homogeneous region more than capable of sustaining a growth. The furnace works as well, and it matches its set point temperature reliably. It's embedded in the system, so the whole system is integrated and ready to run as soon. All we really need to do is get a longer cord to connect to our power supply. And we were able to make 2 interesting ytterbium zinc systems. And really all we need to do going forward is to set up safety and operating procedures and potentially test new and interesting compounds. And I want to thank the 3 people, especially Dr. Kaiaway, Dr. William Lucas Nelson, Dr. Benny Schundelmeyer for helping me so much with this project. Thank you.